So we have one more session today, which is on Gabor multipliers. I want to give you an intuitive understanding of the Gabor multipliers and which operators can be approximated by Gabor multipliers or so. It's again, as I observe, more at the level of what can you do, how can you do it, instead of what is the programming background, which was a little bit more the original plan for this course, but I think it's important to know what you can do with these things. So I start with the standard setting, which is my Gabor family with redundancy 3/2, so 50%. And we know that when you multiply with a set of coefficients, that you would like to have the property that if you multiply with constant 1, which means your Gabor multiplier is just the Gabor frame operator, that you would like to have the identity. Also, you would like to know that if you multiply with a real valued coefficient scheme, so that's behaving like the audio engineer, that you are getting a positive or let's say a symmetric operator, and if your values are strictly positive, you hope to get a positive, definite, and invertible matrix. This is all true if you take the tight window, because then synthesis and analysis are symmetric, and it's very easy to find that the corresponding properties are okay. So that's why I choose the tight window GT, and it's following the method of Guido-Janssen, which is essentially based on the following trick. In a finite dimensional setting, you try to approximate the inverse operator, not just by the Neumann series, which is a slow procedure, but by suitable polynomials with respect to the Gabor frame operator, and you implement the creation of these polynomials in a good way. So if you know that your Gabor frame operator has a range of eigenvalues, and you find a polynomial which behaves like 1/x on the spectrum, then you have good chances that the corresponding polynomial expression can approximate the inverse of the frame operator very well. Now, if you do this, you create a big matrix which has to be applied on a vector. But if you're smart, you find some recursion ways to get the higher order polynomials from the lower order polynomials. And if you're even more smart, you're not computing the big matrix, but you always just think, well, if I would apply on G convolved with the early expression, and you do this manipulation on the G convolved with the preliminary approximation, you get something better. So this is in the background of this tight construction. Now, the corresponding tight frame has the property that GT prime with GT, which is the Gabor frame matrix, is the identity operator. I was just doing this here to convince you that the traditional way, that would be the naive way of take the inverse of the squared matrix, which is the same as square root of the inverse, then you would get this exact canonical tight window. Now, what I'm doing next, in order to demonstrate a little bit what is the other properties of a Gabor multiplier, I was choosing a random set of coefficients, and then I was creating a Gabor multiplier with a large lattice constant. This is made in order to ensure that the individual contributions have not too much overlap, and that you see clearly. Now, the operator that you get is something which is concentrated at these blobs, and these blobs have something to do. So what is this plot? This is the matrix of the Gabor multiplier. This is the matrix for the Fourier transform side, which looks very similar. And this is the Kohn-Nirenberg symbol, and this is the spreading domain. Now, what you see here is that the spreading domain is quite concentrated, and that's also realistic. Every Gabor multiplier arising from a decent window, so G is decent in the sense of smooth and decaying. Smooth and decaying means also concentrated in time and in frequency. means the same as the VGG, the short-time Fourier transform of G with respect to G is concentrated, because this is what you see here. So this is the spreading domain of the rank 1 operator, the PGG. So that's what you could say is here. Now, what you see here is that the scheme of coefficients which I'm using are random values, so real random values in this case of demonstration, between 0 and 1. And you see, well, there are these contributions, and actually it's just telling you that each of these elements is a projection on one of the Gabor atoms. So I was choosing a much too sparse Gabor family with lattice constants 40 and 40. So that's why we have these positions in the lattice domain. They are not good enough to cover. But it tells you that if coefficients, I don't know, 7 and 5, which is in this scheme, go 7 down and 5 to the right, is how much of this projection onto this corresponding Gabor atom is used. So once more, the Gabor multipliers have in the Nirenberg symbol this setting. And it's quite plausible that these projections are quite good linear independent, and you could even decrease this and allow it. Maybe I'm demonstrating it here now. We have maybe 20 and 20. That's the Gabor multiplier routine picks out from our set of coefficients, which is of course a new random experiment. The values at the lattice 20, 20. And now what you see here is this feature is more or less the same. This is also the same. So they are having a vertical profile, which is like a Gauss profile. They are not decaying in this direction. But here you don't see so well how they are separated. Now I can tell you that even in this situation, these blobs, which are overlapping now, are linear independent in the space of images, or as Hilbert-Schmidt operators. So I could say that in this case, they are, and I put it back for the records, in this case, they are still linear independent, and we can determine the condition number of this system. So, and then of course also do this best approximation on this collection of Gabor atoms or so. Now, if I would change from the signal, which was a Gauss function used for the Gabor multiplier, to something which is a smooth signal, so a band-limited function. Here I'm choosing a band-limited function with maximal frequency 80, which means it's not decaying, but it's doesn't have high frequencies, and I create a Gabor multiplier with random things, then this would fill this. But here you will see a space that it's essentially where you would expect the spectrogram of this here. So maybe just as an illustration here, let me do, because this part, the Nirenberg symbol, is not so interesting, or maybe let's go subplot plot 2 to 1, and let's do image STF of RG. So we get a new random signal. And so we will see now the spectrogram described in the same way of a low pass signal. And you see, of course, there are no frequencies. And if you zoom in, it's more smeared. So it's like this here, but it's only significantly non-zero around this strip or so. Now, if I would do something which is a linear combination of the first 30 Hermite functions, so that means it's a very much concentrated function here. Maybe I'm doing the same thing now, but I'm using another window. I take the Nirenberg symbol, which doesn't say much. Subplot 2 to 3. Sorry, 2 to 3. And I'm doing image STF of our new HG Hermite G. Then you will see that these are things which are concentrated near the origin in the time frequency plane. So it's very close. and that this spreading function is a kind of extended smeared version of this. Now, in reality, it's true that you can get this by convolution and twisted convolution from this profile, but this is not so important here. So we have something different here. And now I'm trying to show you that you can represent a so-called underspread operator. So we have seen these 4 different representations of the matrix, the Fourier version of the matrix, which is the same as the same matrix under the 2-dimensional Fourier transform, the Kohn-Nirenberg symbol, or the spreading domain. So since we expect that only something which has a concentration of this form can be represented, we are trying to create a random vector. And observe, I'm doing a very strong zoom by a factor of 8 here in order to make this random thing visible. So what I'm really doing here is I design a rectangular filter with a maximal delay in the time and in the frequency direction. So that's the rectangular filter. And I say, well, give me an operator which is a low pass or low frequency object in the spreading domain. What is the maximal time delay, which is 4 in my case, and what is the maximal in the frequency domain. And show equal 1 means I want to show you this picture. Now, I was trying to test and say, well, can I prove that if I do a filtering in the spreading domain of the given operator t, that it's not changing? So it's like you're saying I have a band limited function with maximal frequency 12, and if I multiply with a constant 1 rectangular filter from -12 to +12 with 25 non-zero values equal to 1, everything would be fine. So I was saying, well, this is the rectangular filter that I do with these 2 parameters, time and frequency. And then I do the other thing, which is I take from this operator the support, which is just computed now. It's not the original one used for construction. I say, because it's random, I take this spreading domain of this, that's the picture here, and I take those where the absolute value is bigger than 1000 times the epsilon. And if I display this, I see I get this, and then my rectangular filter using input number 1 and 2 are this. And that just tells me that we should do this not with this rectangular filter, but with the transpose. Now, I was not sure, and I was just naively doing it in this way when not remembering the details of my construction. But then I decided I can do it by, it's very natural because we're working with matrices now. Matrices means you're describing things in terms of row and columns. So if you think of entries of a matrix, A35 means row number 3, column number 5. And so this is the spirit why we should choose a rectangular filter where the vertical direction is the row elevation, which is, however, in terms of interpretation, the maximal delay. So we are in the relative operation. So it's not time and frequency actually, but it's time shift and frequency shift. So I call it time delay and Doppler shift, so frequency shift, but that's not so important. But then you see that this is exactly the right thing. And so if I say, well, I could do a time frequency filtering of this spectrogram. So this is the spectrogram, this little rectangular picture. And if I multiply now with the transpose of this rectangle, it looks already quite similar. I'm getting the same. And you see it's numerically, it's done computed in a different way, but everything is fine. Now, what I want to explain now is that actually both the construction of a Gabor multiplier so rely on the fact that we're doing essentially a multiplication in the spreading domain, or equivalently an ordinary convolution relation in the Kohn-Nirenberg symbol. So for the explanation here, it's easier to concentrate on the spreading domain. So you're giving me an underspread operator, the only thing that you give me the operator, let's say the matrix T, which, as we have seen, is in this case something which has not too many side diagonals, and each of those side diagonals are actually smooth with maximal frequency, which is corresponding to the maximal Doppler shift. But that's a different thing now. But then in the spreading domain, it will be concentrated here. And we try to create it with the window G. And that's why we have to see if it's possible to get the object, the desired object, which has these random values in the area of the rectangle marked with black stars, by multiplication out of a bump function, which is this colorful 2D Gauss function in our case. So again, we start from two windows, analysis and synthesis with G, which actually means that the construction involves the projection operators or the tensor product of G with G or G prime with G. And that looks like this, and it is a spreading function, which is again up to dilation a two-dimensional Gauss function. So this looks not bad because we are more or less inside the yellow circle, and that means that the values of our bump function are between 0 and 1 in this case. So there should be a good chance. If we have this profile, what we have to do, we have to multiply it in the appropriate way. Now, what we have seen here is that it's looking like a diagonal matrix with a few side diagonals. And in order to illustrate also this effect, I was showing you, I'm doing a side diagonal representation, meaning I put the main diagonal as the first row, the first side diagonal as the second row, and so on. And if I look at the collection of all these side diagonals, I see they all are very smooth and very similar. Well, and after number, we have number 9, which means except from the central position, we are allowed to shift by 8. And remember, we had a parameter here with time frequency shift 8 and 4. And so, well, maybe we can increase this. We increase it maybe just to 9 or 10, and we take the maximal frequency equal to 7. Then we will see now the matrix here is slightly larger. This is a little bit longer and a little bit. We are again zooming in here. Yeah, you see that this is now much broader in the frequency domain. I don't know why this zoom doesn't work, but it's not so important. But what we would like to see is the corresponding rectangular filters. Again, they're a little bit broader. And we have now a larger domain. And this has to be done again. And now I think we should see, oh no. I think that was, we have to renew this cyclic mat here. And we will see that now it should go for higher frequencies. Yeah, I see I was increasing by 2 so that you can see that there's the further one are not here. And the frequencies that are appearing here are now larger. Now I can count in this new representation of side diagonals, what are the row numbers which are non-zero rows, and then this is profile is here, so I'm just using a command which computes the row norms. So it goes from row number 1 to 3, and you see the first and the last one are okay. That's why I'm doing the plot C command, and then I'm trying to tell you how can I do the Gabor multiplier approximation. So the Gabor multiplier can be written, as I have shown you in the first picture, with this large lattice constants A equal B equal 40, as a projection on a linear combination of bump functions, which are the Krohn-Nirenberg symbols of the projection operators on our atom. Now recall, we have seen there are blobs. In reality, for the Gaussian case, they are really just two-dimensional Gauss function. And if you take dilated Gauss functions, it's an eccentric version of this with elliptic profile. But the question is exactly analog to the approximation of a function by spline type spaces. So this is what we use for implementation. So how do you use this? Well, you realize that this collection of shifted versions, so the Korn-Nirenberg symbol, moving from one projection operator to the other projection operator within our Gabor family is just a translation. Therefore, there is some Gram matrix involved, which is circulant matrix. The circulant matrix, of course, can be inverted by using an FFT. So you never have to build a whole big system, which would be a huge matrix, but we just do this. So in this way, you can say, well, either we are, I mean, that's maybe the best thing. We are taking this to the spreading domain and you try to approximate the Korn-Nirenberg symbol of our operator. So this was something like this here, and it looks nice, which is smooth. By linear combinations of Gauss functions, where now, in our case, the lattice constants are a little bit different with this a equal 20 and 16 or so. Now, if I look at the result of the command, so what do you need as ingredients? You say, I have a matrix. So you're saying, I have an operator, which in our case is represented as an ordinary matrix multiplication from the right of format n by n. You're describing the Gerber system by saying, well, I would like to use the atom G and the parameters A and B, and then please give me the Gabor multiplier, which is the operator written in this way. But of course, if I want to study it, I would like to know the coefficients. And so the thing which I was just preparing was, I can ask, is the operator exactly or very well approximated? And in the operator norm, what I find, it's approximated up to order 4%, I mean, 4%, I don't know if the operator itself is normalized, probably not. Maybe we can compute this. So what is the norm of the Gabor multiplier approximating the t compared to the norm of t? That's maybe more relevant. Yeah, I didn't reactivate this command. Maybe we should do it now. Yeah, so, okay, so this is not so good. It's 50%. Yeah, well, in this case, we should probably look at the difference. Yeah, I think it would be interesting to look at this. Yeah, I think the problem was that I have increased our rectangle so that we have a problem here. But let's look at the Korn-Nirenberg symbol. So what is centered image? The Korn-Nirenberg symbol, so convert from matrix representation to Korn-Nirenberg symbol, the difference, and we should start a new figure. And we will see where this error comes from. Yeah, okay. So it's, well, actually quite significant or so. We could also try to see where is the error in the frequency domain. So instead of KNS, we would look at the mat to spread function of the difference, but we know it will be concentrated. So we do just a strong zoom. We do a plot X, maybe yellow, and try this also. Yeah, okay. So I think what was the A and the B? Yeah, Maybe this was the problem, that they were too big or so. I don't want to change it now, but you can imagine that there must be some problem that I didn't have in the preparation, because you see here, now that it's a different thing, whether it's still true that if I compute the Gerber multiplier with atom G and the coefficients which we have obtained, then you really get the Gerber multiplier. So that's actually what we are doing here. We're computing the coefficients of the best approximation by inverting some, with FFT methods, some big two-dimensional gram matrix, but it's cheap because it's a two-dimensional matrix or so. Okay, so I think that's at least a very quick summary of what we can do with the Gabor multipliers, and therefore I'm finishing my records now.